All right, here is a look at kind of the Unit 3 content. I'm basing it mostly off the type of problems you guys have on that Unit 3 Homework 1. And to look through these problems kind of opens up some doors to big concept questions. The derivatives aren't terribly difficult, and how we deal with slopes of tangents that derivatives do give us isn't too difficult. It's the type of questions that can be asked and trying to keep your bearings straight on how to go about these. So the first question, estimating slope. So just a general sense of you need to know the slope. A graph like this, if you have a horizontal line, then you get a slope that's equal to 0. That should be an m equals 0. Sorry about that. But anytime a horizontal tangent, that'd be a slope of 0 versus something that you have some kind of, at x2, y2, kind of a slant to it, a pitch of some sort. Then you want to do your regular, find 2 points and do rise over run. So 3/2 would be a reasonable estimate of that. And I think it'll give you a little give and take there. But if you pick 2 points, you can ballpark it, and that should be good enough. Then when you get to the next one, it says, if you look at this particular graph, you're going to compare secant slopes. And one thing you need to recognize is that in A and B, you're talking about the slope of a secant line here. No derivatives going on here, no calculus per se. But you are trying to find out what the slope of a secant line is compared to another. So in part A, f of 5 minus f of 4, you need to have f of 5 is that point up there. It's 5, 6. You put some color in there. So that's the first point right there. That's your, let me try it a little bit better. That 5, 6 is your f of 5, and what you get out is 6. And then minus f of 4, and f of 4 is that point I've located there. At x equals 4, the value of the function f of 4 is, and that's something you can kind of estimate. I will here in a minute do it. I'm going to guess it's about 5.5, roughly between those two. So once you do that, then you can go about answering this. Either just take a look at it and say, now the first one is taking the slope between those 2 points right there that I've indicated, so a little slant line, versus going between f of 5 and f of 1 and doing a slope between those 2 orange ones. So if I go on the top 2 versus the top one and the bottom one, there's a difference in their slant. Now you can do it numerically, or you can do it a little more, calculate it with estimating f of 4 is 5.5 is good. I'll do both. So if you do numerically, and I put them in there and I just grab that, and so I've taken these numbers here, color-coded a little bit, and I just approximated those values. If you want to compare them that way, it's pretty obvious which ones are which. Or if you just draw in the lines, the red one indicating the first secant, the blue one in the second one, you can just say, yeah, it's pretty obvious. The blue one's steeper than the red one. But if you want to put the numbers to it, you certainly can as well. And I get 1/2-ish and 4/4, which is 1. And you can definitely see which one's bigger. The blue line is steeper, has a bigger slope. Before I do go to that, I'm going to go back 1 second here. That last question is the slope of the tangent, f prime of 1 means the slope of the tangent at 1, and I didn't draw that one in there. Let's go with some standout color, like you want to compare the f of 5 minus f of 1. That's our blue slant, so if I got the colors in here right, I'm comparing that blue slant to that secant slope to my f prime of 1 tangent slope, and who's bigger? My tangent's got a bigger slope to it, so the inequality is going to be such that the blue secant has a lesser slope than the green tangent slope. But f prime of 1 means the tangent at x equals 1. Okay, so then to the next piece. It does say limit process on these. We're done with that. You can move on. Derivative rules are great. And this one requires that algebra beforehand. You don't want to just derive this straight up. You want to remember, if there's an opportunity to rewrite it, you should. Like 4 over x squared is 4x to the negative 2. And it helps you open up the power rule and makes that much easier. The derivative of that, straight and sweet, f prime is simply negative 8x to the negative 3rd. You can leave it like that. That's fine. But you want to go for bonus points by moving the negative exponents to the denominator. That'll help down the road. So think of having that in your back pocket as well. Both of those go into WebAssign without any issue. The next one, same thing, derivative methods. Don't overthink it. Just straight up power rule. Move on. Some of them are easy. Enjoy them. If you go to the next one, derivative methods. So if I look at a line, y equals 1, that's what this is, a horizontal line. It has a slope of 0 everywhere. That's one way to think of it. Or, the derivative of a constant is 0. So either one you want to go through. Think of what the graph looks like. Horizontal line, slope of 0. The derivative itself produces a 0. Any derivative of a constant is 0. Both are fine ideas. The slope of the tangent line question is two-part. One, you need the derivative to find the slope of a tangent line. Actually, this one's a single part. If it was phrased equation of a tangent line, then you have two parts. Let me say that again. Slope of a tangent line, straight up derivative, put in the value of x that's necessary. If I say the equation of a tangent line, then you've got some work to do in the process. We'll get those later, but this one's just read carefully, find the slope of the tangent. Hey, that's what a derivative gives us. Let me get the derivative. Let me put my stuff in. So I've got it. In this case, the derivative is 5/3, which is constant, and that messes people up. You're thinking there's no x in there, which means, yeah, your slope is the same no matter what x is. A line has a constant slope, so it's always 5/3. So there's no place to put it. That's okay. If you do have an x sub in, then sub the x in. If not, then take it as a constant and all is well. And then next one, nice little parabola. Here's the equation of the tangent line. Here's where, all right, we're going to get, and then it talks about parallels. All this just to mess you up. The thing is we learned some calculus for one job. If you take the derivative, it'll give you the slope of the tangent line at any x you want on f of x. Then a separate line that's given to us is a measure of what kind of slope we want to get. And it's saying I want a tangent line that's parallel to this given line. And the parallel line, I need to find its slope because that's like the slope I want. That's like that's the value I'm most interested in. So there we are. I solve for y, just added y to both sides. The slope of that line, which is not on the function, I'll graph it for you in a minute, has a slope of 4. It's just a line with a slope of 4, y-intercept of 4. Now what I want, it says find any equation that has a parallel slope to, and is also tangent to 2x squared. So it's not just I want it to be have a slope of 4, I need it to also be tangent to 2x squared, touch it in one spot. So 4x plus 4 isn't tangent to the x squared graph, it just cuts right through it. Where else could I put a line that's tangent to the parabola, touches it in one spot, just teeters on it, but still has that same slant of 4? That's the question at hand. So when is the tangent line slope to f of x equal to f prime of x? That's what I'm going, equal to 4, I'm sorry. Okay, so put it in there, when's it equal to 4? We're going to find out. There's a way to do this. When's the tangent line slope to f of x equal to 4? I actually need to set up an equation. Tangent line slope to f of x means f prime of x. When is it equal to 4? Means I'm going to put f prime of x and set it equal to 4. So here's f prime of x. Nice easy derivative, 4x. When is it equal to 4? You set it equal to 4. And you solve for x, and you get 1. So that means at x equals 1, you're going to have on that f of x graph a tangent line that's parallel to that red line. It'll have a slope of 4. And you can kind of see it just drawing even a sketchy sketch. Well, that's all fine and good, but I don't just want to know where it's located at x equals 1. I want to know the equation of it. And the thing is I only know one part of that line. I know that its slope is 4. I need to get its y-intercept. That's the other part of the equation. So one of the things I need to do is get all the information I can. At x equals 1 on that graph is where the tangent is. I also know I can get the y value, plug it back into f of x. Crosses at 2. So that's the point 1, 2. It has a slope of 4. I know a lot of stuff. The equation is putting that together. Put the 4 in for the slope, because I got that. But I also need to sub in the point I know, 1, 2, and then find out what the y-intercept is that goes with it. That takes a long time to get your brain straight on all the pieces that need to happen there. The derivative gives you a slope. The line parallel is just a mark saying I need my slope to be 4. Then you find out where it's located. You need to get the y-coordinate, go find it. If you need the slope, go find it. If you need the y-intercept so you can get the equation of that line, just plug in what you know and go find it. So there's a lot of things to think about. And in the end, if you solve for that b, you get -2. And there you are. That's your equation. Type it in and you're good to go. All right, so I'm going to go to 10 minutes, one more problem, and then I'm going to go and send you part 2 later. But you can't determine the slope at a cusp. So those are cusps. Well, I guess you'd call those corners. So if I go down there, there's a, we had that, I think in one of your classes we talked about cusp versus corner. Cusp would mean the slope on either side is essentially the same. Corner is when you have kind of like a curve going into a straight line graph. And I don't know. This one, it's kind of hard to tell just looking at it. It kind of looks like they might have the same slope on both sides. So I'm not going to beat you up on the definition there. You just know that when it comes to some type of corner or cusp, however you define it, the derivative is undefined because you can't really place a tangent there equally or in a singular way. You can actually send it many ways. So it's undefined. It says differentiable. It's weird how it's written. The function is differentiable for all x not equal to plus or minus 8. It's a way of saying for everything but plus or minus 8. Funny way to word that. And then finally, I'm going to prompt this one and then say, hey, let's watch video 2, because this one takes a while. So go back, pause, stop, go back and replay any of that. I went fast. And then look for video 2 that gives you more information.